Okay, cool, amazing. Hey everybody. Thanks so much for being here. My name is Camila Ramos, and before I get started, just out of pure curiosity, how many people here either work or are interested, like more than kind of a hobbyist in crypto or blockchain, and how many people here, okay, cool. So then everyone else, I would say, is it safe to assume beginner, intro level stuff? Okay, cool. I just wanted to get a read on the room. Amazing. So today we're going to be talking about blockchain scalability and the architecture for widespread adoption and kind of what that means today, what scalability looks like in terms of blockchain and the current state of scalability, existing solutions, and kind of what we're working on at Fuel Labs. There we go. Okay, cool. Real quick about me, I'm an educator. I love teaching. I've spent the last 6 or 7 years teaching K-12 technology education. I've spent a really long time teaching kids how to code, and I just really believe in access to specifically coding education. I started off my career in a very traditional path. I studied computer science in college. Then I went off to be an engineer at PayPal, where I worked on the checkout experience, which is the pay with PayPal button that you see on all of the merchant websites. And now I'm the head of DevRel at Fuel Labs. So the intro was actually older. Before I was at EduNode, now I'm at Fuel Labs. Whatever. Okay, cool. So we're going to be talking about layer 2s and modular blockchains specifically, and here's the agenda for the day. So how do blockchains work? What is scalability? The challenges with the existing architecture of blockchains, which we'll call monolith, and we'll talk more about what that means in a second. Existing approaches to scalability and kind of the trade-offs between all of them, and again, what we're working on over at Fuel Labs, modular execution layers, and modular blockchains. Let me try this one more time. Okay, cool. So buckle up. This is going to be a pretty technically dense talk, and this is me trying to distill months and months of research and learning and understanding into a 30-minute talk, which now we have 28 minutes of. It's going to go a little bit fast. I'm going to use up the whole 30 minutes, so Q&A will be done off stage, so just keep that in mind. Amazing, yeah. Thank you. Okay, cool. Starting from the beginning, I just want to make sure we all start on the same page. So for people who are newer here, so blockchain 101. So transactions are batched into what are known as blocks, and they're connected to each other to form this chain. And when we say transactions, we mean write operations, kind of is like the term that you might use in Web 2, where it's like anything that is actually writing. So reading is not a transaction, and we'll talk more about exactly what this means in a second, but just keep this in mind as our base definitions as we move on. Ooh. It's skipping. There we go. So what I mean by updating state is that, so the chain has this global state, and then we execute some transaction that does some computation to process and give us a new state. So for example, this means any account owned by a human. So all transactions are actually things that humans, we press a button, we send money, we execute some contract, we deploy contract. That's what we mean when we say transaction. So for example, Bob sends Alice 1 ETH. That's a transaction. There's been an update to the state, and now the global state of the whole chain changes. Oh, it did work. Okay, cool. So the best definition that I like to use for a blockchain is that it's a decentralized public database and peer-to-peer network. There's a lot of different definitions out there, and they all are correct, and they all kind of have different nuances, but specifically for what we're going to talk about these 3 terms separately so that we can get into the architecture and how it makes sense. So the first point is decentralized. So it's decentralized in the sense, as you know, it's this public database that is stored among many different nodes. But the very important thing to know, and it's like a small difference, but it's a huge difference, is that the state of the chain is not it's replicated but not distributed amongst the different nodes. So there's a difference. So distributed, right, you might think like, I don't know, one node has like 1/100th of the chain, and then the other node has 1/100th of the chain, but that's not the way it works. In a blockchain, it's replicated. So every node holds the exact same state. And that's like the difference that we're going to know as we move forward, and kind of what this means for scalability and the bottlenecks that exist because of this very specific definition. Now, the next one, public database. So yeah, all of these transactions take place, and the chain holds this global state of all the things that include things like the balance of people's accounts. So if we have all these different transactions, then we have to keep up this ledger and say, okay, for this last transaction, Bob sent Alice 1 ETH, so now Bob's balance needs to be decreased by 1, Alice's needs to be increased by 1, and this needs to be replicated, and all of the nodes need to be on the same page about this new chain. And finally, peer-to-peer network. And what this means is that every participant in the network can directly access every other participant in the network with no intermediary. So that means I can send and receive data to any other participant in the network directly. So this could mean something as simple as like executing a contract or directly sending money. So if I wanted to send money to a user in Colombia, where I'm from, I wanted to send them some ETH, there's nothing that they have to do to kind of get permission or access to use this network. They just create a wallet, and that's it. Okay, so now that we're all on the same page on kind of what we mean when we say blockchain, let's talk about the blockchain functions. So I'm not going to get too in the weeds here because this can get very, 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 very in the weeds. So at a very surface level, there's 4 functions that a blockchain does. The first one is execution, which, like I said, is computation over transactions that produces a new state. The next one is data availability, and this means that nodes download the data to ensure it's available. And the reason why this is important is because, again, we'll talk about this more, but a core feature of blockchains is this idea of user sovereignty, and users themselves being able to validate the chain and say, yes, this is correct, yes, these transactions actually did happen this way. Because if not, right, then you kind of end up back in the paradigm that we're in now, which is like, yeah, I'm going to put this money in the bank and trust that the bank will hold on to it. I'm going to put this money in the bank and trust that if there's like some sort of civil war, that the bank is not going to block me from getting it. So that's a core feature, and that's kind of the basis of data availability, is that you have to make sure this data exists so that you yourself can verify that it happened the way it did. Now, consensus is the order of the transactions so that we can all agree this happened first, this happened second, and kind of the algorithm, which we can get into later, about what exactly makes a transaction valid and how it can be added to the chain. And then finally, the settlement layer is to dispute resolution, which we'll get a lot more into in a second. So scalability in kind of traditional applications is defined as the ability to handle a growing number of users without taking a hit on performance or causing disruptions to the user experience, right? So the same ethos applies to blockchain, except there's a very specific definition for what it means to have a scalable blockchain. So a scalable blockchain, oh man, keep skipping, there we go. So scalability in blockchains is defined as the ratio of throughput over decentralization. So throughput is transactions per second, which is the load that the chain can handle, the number of transactions that this chain can execute, over decentralization. But now, what exactly does decentralization mean? When I was first starting out, this was very like philosophical, and I was like, okay, this idea that it's like it's ours and it's everyone's, but it's no one's. But really, there's a very specific definition of decentralization. Decentralization is the cost for an end user to run a full node. And this goes back to the idea of user sovereignty, which is the ability for an end user to validate the chain themselves and not trust any other party to say, okay, yes, the majority of validators are being honest, and therefore, I can make that trust assumption and say, I'm going to trust this assumption, and you kind of just hope that always works out, right? But true decentralization is this idea that you don't have to trust. You can make the most minimal trust assumptions, and you yourself have this validation of security. So talking about full nodes, what is a full node? I just said it's the cost. Decentralization is the cost for an end user to run a full node, but what does that mean exactly? So there's 2 types of nodes that we'll talk about here. A full node is a type of node that downloads and executes every transaction locally, verifying the validity of the chain. So this is the most maximum security that you can get, because literally your node is going to take days to sync, but it's going to download every transaction and execute it and say, yep, this matches with what the chain has. There's 100% certainty that this is correct. The other type of node is a light client, which instead of downloading and executing all the transactions locally, it only downloads block headers, which has some summary information, and then those light clients can use that information to request more information from light nodes. But it's not as secure because you're not actually verifying those transactions yourself. So we'll keep these 2 in mind, and this is kind of the core of where we get to scalability and the different approaches that exist for it. Okay, so back to this, right? So we said maximum security, being able to run a full node. Now over here, when we're talking about decentralization, again, the nodes have to be able to handle the volume of transactions for the whole chain, and this imposes a limit on what the chain can handle. So we'll talk about this later, but there's something you can do where you can say, oh, let's just make the node requirements higher, and therefore we'll get more throughput. And that's something that some chains do. But remember, when we're talking about decentralization, we don't want to give up decentralization. We don't want to give up the core part of what makes this technology kind of different from other things. So you have to remember there's this thing that we all agreed on through social consensus, aka we all sat down at a round table and said, what we want to be the core of this is that everyday users can validate the chain. So we all agree that there is a limit to the hardware that we can use to do compute for this chain. So throughput is constrained by the resource requirements of a single node, remember, because the blockchain is replicated and not distributed. So when I was first starting out, I was like, oh, well, we can just add more nodes. Or maybe in 10 years when blockchain's gone mainstream, there'll be like 100 times more nodes, and then we'll have more scalability. But no, so it's one single node. So again, back to this topic, you could increase throughput by increasing bandwidth, compute, and storage capacity, which a chain like Solana does, where if you wanted to run a full node for Solana, you wouldn't be able to do it on consumer hardware. So again, it goes back to this, like, yes, you can do it, but people like me and you would have to go buy specialized equipment to be able to run a full node and then validate the chain ourselves. So this isn't exactly scalability. And when we talk about Solana, when we talk about Ethereum, these are all what I'll call from now on monolithic chains. And in this architecture, the chain does all 4 of those functions that we talked about earlier in one single layer. So it handles execution, consensus, data availability, and settlement all in one chain. And what we're going to talk about now is kind of a different approach and what would happen if you try to separate these into different layers. So before we move on to that, let's talk about some of the existing challenges that come with scaling a monolithic chain like Ethereum or Solana. So the first one is that it's costly and inefficient to do transaction verification. Like we just talked about, you have to download all of the transactions, execute them locally. Like I said, it takes days for your node to sync. Like if you went home and you're like, I want to spin up a full node, I want to take part in this, it'll take a few days for it to even catch up to the tip of the chain. And that part alone is like, it's not really efficient. The other one is that it's constrained by the resources of the blockchain, remember, by a single node. So throughput is constrained by the resource requirements there. So that's something that, like I said, we agreed on. It's not something that we can change because at the base level, we said, we are putting hardware limits on what we're doing, and we're going to build from there. We're going to figure out other ways to scale. So that's another one. And then the other one, which is kind of the key point here, is that the node is sharing resources amongst all these different functions. So in this monolithic architecture, the 4 functions are operating on the same finite set of computing resources. So for example, using a node's capacity for execution means that there's less capacity left over for data availability and all the other functions. So all sharing this finite set that we have agreed on. So now let's talk about some of the existing scaling solutions that are out there right now for blockchains. We'll talk about the pros, we'll talk about the cons, and we'll take a look at all of them side by side and then kind of introduce this new one that we're working on at Fuel Labs. So the first one are called optimistic rollups. So rollups are blockchains that perform transaction execution outside of the layer 1 and then post their blocks to the layer 1 where consensus is reached. So what happens is they just assume it's valid. They don't say, is this valid? They don't try to check it. They just execute them and then post the blocks. And the reason why it's called optimistic is because then we're making this optimistic assumption that, yes, they are valid. And one of the things that you have to do there is there's this concept of a challenge time, where there's a time period where anyone can challenge the transaction's validity and say, hey, I'm running a full node. I executed this locally. I don't know, transaction 1, 2, 3, 4, 5 is wrong. They got 6 and I got 7. So in that 1 week, all of us who are running full nodes have time to say, I'm going to check this and make sure it's right. After that time period has ended, then you can pull out the funds. So that's one of the cons, is that there's a delay in withdrawing funds, so it's like not the best solution, because if you're doing execution on some of these rollups, like Optimism and Arbitrum are some examples, they do like get you a lot faster throughput, but you're also going to have to wait for that challenge time to be over. Another scaling solution are state channels. So state channels also do compute off-chain, and really the key thing to know here is that they use a multi-sig contract, which we won't even get into the weeds because it doesn't matter, but the point is, people have to sit down and say, hey, let's use a state channel to do this transaction. I want to build this decentralized application, or I want to do this very specific task. And kind of the con there is that it only works for situations where people who are participating are predefined. So if I'm creating a state channel and then someone says, oh, I want to do a swap or I want to participate somehow, we would have to create a new state channel. So it's not really scalable and it's not dynamic. It only works for very specific use cases. Another one are side chains, and the one that people are probably most familiar with is Polygon is an example of a side chain. So it's an independent EVM-compatible blockchain which runs next to the layer 1, in this case Ethereum's mainnet. And the pro is that because it has its own consensus algorithm, or because it can have its own consensus algorithm, it can be designed for more efficient processing of transactions. So it can kind of make up its own rules and say, I'm not subject to the security and consensus algorithm of the mainnet, and therefore I have the freedom to design them in this very specific use case where I want to optimize for transaction processing. But the con of that is that you don't inherit the security of the L1, aka you don't post blocks to the base chain. And that in itself is like losing a lot of the decentralization. Okay, let's see if it works this time. Okay, and then finally, for existing solutions, ZK rollups. So earlier I talked about optimistic rollups. They're a type of rollup. This is another type of rollup called ZK rollups that uses zero-knowledge proofs to produce a cryptographic proof that this block or this transaction is valid. So the pro is that it's super fast and it's super secure because you can prove zero knowledge that yes, this is correct. There's no way it can be wrong. There's not this concept of a challenge time. You're not being optimistic and just saying like I hope this works. But the con of it is that the tech is still not mature and it's still not in a place where we can really use this, and it's still a work in progress. So a lot of this is like a lot of this can be considered kind of theoretical, where we're pretty sure it's going to work this way, and we're pretty sure it's going to be fast, and we're pretty sure it's going to be scalable, but we just don't know yet. Okay, now, moving on to modular architecture. So we talked about monolithic architecture, we talked about some of the challenges, and then we talked about scaling solutions for that very specific architecture type. Now we're going to talk about a new type of architecture called modular architecture. So modularity allows the key functions of a blockchain to be separated out and into specialized layers. So now, one thing to note is that modular blockchains don't inherently create a new sense of scalability. Not inherently. It's the properties that get derived from this architecture that can make it more scalable. So that's one thing to keep in mind, is that you might hear people, modular blockchains are kind of taking off now. They're really coming into center stage in the blockchain world. And a lot of people think that, just by modularity, there's like some magic happening under the hood that makes them more scalable, but that's not true. It's different properties that can be derived from this architecture. Now, one key, which is also not inherent to modular, but it's basically like if the teams are good enough, there's this assumption that if you can specialize these layers, then these layers can be better. Because instead of a team having to be an expert on consensus, on execution, on data availability, on settlement, you can get a team together that's really good at execution, or you can get a team that's really good at data availability, and therefore potentially have more performance at these layers. So what we're going to talk about specifically today in terms of scaling is a modular execution layer. So a modular execution layer is similar to a rollup in that it's a blockchain created specifically to handle transaction execution. So block out all these other ones. We say some other team is going to make a really good layer for data availability, settlement, consensus. We're going to focus on making a really good layer for execution, and then we can build out this modular stack where we have specialization, we have a good team, so we're going to have some gains from there, and then some gains that are the derivatives of this architecture, which we'll talk about right now. So I work at Fuel Labs, which is building Fuel, the fastest modular execution layer that delivers maximum security and highest flexible throughput for the Ethereum ecosystem. Okay, so here's where it gets really technical, and I feel bad, but I'm doing my super best to really get this down into a very concise explanation. I link resources at the end where you can read more in depth and kind of read through white papers and read through other resources, but here we're going to try to get this down in 10 minutes. So, modular execution. Fuel was built for these things called fraud proofs, which is what we use in optimistic rollups. This concept of we're going to assume that they're valid, and then we have this challenge time where anyone can challenge them and say, hey, this is not correct, and then they're ignored. So it's built for fraud proofs, which enable this thing called trust minimized light clients, which enable high security without requiring high resource usage. So do you remember earlier we talked about full nodes versus light clients? The light clients that we discussed there are kind of nicknamed or called there's this trust assumption, right, where you say, I'm going to trust that the majority of validators are being honest, and therefore I can trust them. With trust minimized lie clients, you don't make that assumption at all. The only assumption that you make is that there's at least one honest validator. So it's a different trust assumption. There's still a trust assumption, but the trust assumption is minimized, where you're saying instead of trusting that like 6 out of 10 are honest, which you hope for, you can say, I'm just going to trust that 1 out of 10 are honest, which is much more likely. So if you look at this graph, all the way on the right side, you see this full node, which is what we talked about. It's the most secure, but it also requires a lot of resources, computing resources. And then we talk about the honest majority lie clients all the way to the bottom left, where it doesn't require even close to many resources, but it's not as secure, not nearly as secure. And now you see trust minimized lie clients are almost as secure as full nodes, but require almost none of the resource requirements that a full node does. And that's kind of the beauty and what we're going to talk about, how this enables scaling. So fraud proofs, just kind of going back here. So security model where transactions are assumed to be valid after this challenge time. They are definitely valid. But the key thing here is that fraud proofs allow users directly to know that the chain is valid without having to execute the transactions locally. So instead of you having to download all of the chain from Genesis and like execute all this, you can say, I'm just going to use this security model and rely on fraud proofs, because if they're incorrect, I'm going to be able to either submit one myself or someone else in this network is going to be able to make a claim on this transaction. So now, what does this mean? Like, how does this mean scalability? Because we have fraud proofs, now users don't have to run full nodes to have high security with minimal trust assumptions. Now users can run trust minimized lie clients and have almost the same security. And really what that means, I put this back here so you guys could kind of recap. I'll leave this up here while I talk. But really what this means is, remember, the initial social agreement was we want to make it so that everyone can validate the chain, and at the time, the only way to do that is to have these things called running full nodes. But now that we say you can get almost the same security without having to have those resource requirements, we're not constrained by the need to keep resource requirements low for nodes, so we can increase node requirements. So we can say, now we are going to do maybe something like Solana, where they can have increased node requirements, and that gives you more transactions per second. That gives you more throughput. But unlike Solana, you're not sacrificing decentralization, because end users can still validate the chain themselves. So by keeping this resource requirements low, we can increase node requirements, which means more computing power, which means more throughput. The thing to know is that at Fuel Labs and modular blockchains, like I said, it's really coming into center stage, but a lot of this technology and a lot of the stuff that I'm talking about is new and experimental. It's something that's only been worked on for the last couple of years. So that's similar to the ZK stuff. It's something where we're like, we think this is going to happen. Based on our calculations, we think this is going to happen, and we think we're going to have these performance enhancements. But at this point, we don't know. So Fuel just launched our testnet, which is basically a developer-facing net that's not mainnet, where you can, learn how to build dApps on Fuel. You can experiment with parallel transaction execution and a bunch of the other features that we offer, which I'll talk about now. So the thing that makes Fuel different maybe than EVM and other chains is 3 kind of core concepts. One is that we have our own Rust-based DSL, which is a language created specifically for blockchain development. And it's based on Rust, and I think people here know and love Rust, but you get a lot of security and a lot of features that you don't really get from Solidity, like the compiler pointing out things and being like, this is wrong, I'm not even going to run. And because it's a DSL, because it's made specifically for blockchain development, the compiler team can say, okay, we are going to be, we're going to create awareness for common types of attacks or common types of bugs like reentrancy attacks. So if you're writing in Solidity, the compiler won't warn you if you're vulnerable to a reentrancy attack. And usually in the blockchain world, companies have to pay hundreds of thousands of dollars to auditing firms who then audit their contracts and try to get them as much security as they can so that they're not vulnerable to a hack. But with Sway, which is the name of the language, which is based on Rust, you get a lot of those really cool features just from the compiler, and you get a lot of that security directly in the compiler, and you have to rely a lot less on the brains of auditors. The second thing is that the Fuel VM, our own virtual machine, is based on the EVM, and it basically learns from what the EVM and the Ethereum community has done over the last few years. So the main thing is that it applies and implements a lot of EIPs, which are Ethereum improvement plans, which basically the community can say, I have this idea for how we can make the chain better, faster, more secure, etc., and I'm going to put this proposal up. The community can vote on it, decides on it, and says, yes, this is good. So there's a lot of EIPs out there that the community has been like, this is really good. For example, parallel transaction execution. Ethereum doesn't have that. everyone's like, yes, this would make it a lot better, but due to the need to maintain backwards compatibility, they just can't implement it. They're bottlenecked by certain, tech debt that they have where they can't implement certain things. So what the Fuel VM did is said, we're going to take all of the positive from the EVM and then implement, literally we went through a list of EIPs and did all this research and said, we're going to take all the EIPs that the Ethereum community wants, and we're going to implement them into this VM. And then lastly, the thing that I really love about Fuel and kind of what drew me there in the beginning was this idea of a superior developer experience. So how many of you guys write in Solidity or have ever tried to write a smart contract? Okay, so a few people. So if you've written in Solidity, the ecosystem is a bit fragmented. So one team created Solidity, one team created Hard Hat, a different team created Foundry, a different team created Open Zeppelin, a different team created these plugins. And sometimes it's hard to find compatibility. Sometimes versioning doesn't work with each other, things get out of date, and it's just pretty fragmented as a developer. It can be frustrating. So with Fuel, they were like, we're going to create this whole ecosystem from the ground up where everything can be vertically integrated and have this just way better flow where you don't have to work on oh, how do I make this talk to this, or how do I make this version work with this version because it's the only version that works because they had to roll that version back. We're just let's just create the entire ecosystem and the entire tool chain so developers have a really smooth and terrific experience when building. Okay, additional reading, I'll leave this up for a little bit in case anyone wants to scan the QR code. I'll also publish these on my Twitter so you can actually click the link and read these yourselves. But the two things that I would recommend are the Fuel book, which goes more in depth on a lot of the things I just talked about: parallel transaction execution, the UTXO model, trust minimized light clients, fraud proofs, the Fuel VM, Sway. There's a developer quick start there, which walks developers through building a dApp on Fuel from end to end. So it'll walk you through building your smart contract, writing tests for it, and building a front end for it. And like I said, I'll publish these on Twitter, so if you don't get a chance to take a picture right now, don't worry. And I actually realized I talked really fast, so I actually have 3 minutes left over for questions. So if anyone has questions, now would be a great time. I think they're going to bring you a mic, yeah.
Thanks for the great overview. Do you have any idea the light client that is going to be implemented in Ethereum with Verco trees and all that, how it compares in this graph of security versus resources?
I actually don't. I'm not super familiar with the new light clients that they're building for Ethereum in specific relation to how it compares on this graph.
Okay, thanks.
Okay, cool. Well, if no one has any questions, like I said, I'll be around over here, maybe right outside in the hallway if anyone wants to chat. And thank you.